Okay, so the last talk of this session is about quantum control programs. Please.
Hi everyone, I'm Charles, and I'm really excited today to share with you the research that we've done on some of the fundamental challenges of programming a quantum computer. This is joint work with my collaborators Aggie and Mike at MIT. So to start, what is a quantum computer and why do we want to build one? Well, in short, a quantum computer is a device that exploits the properties of quantum information to solve problems faster than any classical computer can. Specifically, quantum algorithms are known that can deliver asymptotic advantages for a variety of tasks, ranging from factoring numbers and breaking cryptography, to solving large systems of linear equations, as you might find in machine learning or optimization, as well as physical simulation for chemistry or physics. And the way these algorithms achieve that advantage is by exploiting quantum information. Whereas a classical bit can exist either as the state 0 or 1, a quantum bit or qubit can exist as 0 and 1 simultaneously, in what's called a superposition. So on the slide here, I presented the math for a superposition. It's a linear combination of these zeros and ones. You'll see these funky looking angle brackets, which are called kets. Physicists use kets to denote quantum information. So whenever you see something inside a ket in this talk, just think that's being encoded inside the qubits of some quantum computer. There are also these coefficients in front of them, which are called amplitudes. They kind of denote how much 0 or 1 there exists inside the superposition. And one thing that it tells you is what actually happens when you take Schrödinger's cat, which is both alive and dead at the same time, and open the box. You'll get a classical outcome, in this case, either 0 or 1 with some probability. Okay, so this process is called measurement, and it is probabilistic. The probability of seeing 0 or 1 comes from, it turns out, the square of the norms of the amplitudes. So the amplitudes are actually complex numbers here. Unlike classical probabilities, which are real, amplitudes can have signs, which in this case is called phase, like the phase of a wave. I won't get too much into the depths here of what that means, but the ability for quantum information to be in superposition and have these signs and phases is really important for algorithms to get that advantage. These algorithms have received renewed attention over the last few years because in the last 2 years, we've actually made huge strides in building the hardware that will be necessary to execute these algorithms on real quantum computers at scale. But the question that I want to examine today is not specifically how we build the hardware, but rather how we're going to program these computers. So imagine that you're a developer who's interested in implementing Shor's algorithm for factoring large numbers. Okay, so you can open the paper, and you'll find a mathematical description of how the algorithm works. It has some notation and some English text, basically. And I'll go ahead and summarize for you what's going on here. This is actually the computational bottleneck step of Shor's algorithm, which is doing modular exponentiation. We have integers a and x, and we want to compute x to the a mod n. The way the algorithm does this is by repeatedly iterating a modular multiplication by x mod n. Now, as a programmer, whenever I see a pattern like iteration, I tend to reach for a for loop when it comes to implementing this operation as a program. And indeed, if this were a classical algorithm on a classical computer, you could probably do this in about 1 line of Python code. Okay? But how hard do you think it is to implement this part of Shor's algorithm in a state-of-the-art quantum programming framework? Did you expect it to be this hard? Okay, so this is the implementation of that part of Shor's algorithm in Microsoft's Q# quantum programming framework. The text is extremely small. Let's blow it up and see what's going on. And when we do that, we'll notice that the reason the program is actually so complex is because the abstractions that the program is manipulating are individual logic gates. For example, there's that X gate, if you look in there, that is being controlled on the values of individual bits. So there are some other examples of algorithms that are specified like this. Okay, it's in the form of a quantum circuit, a sequence of individual logic gates acting on individual qubits. That is the standard for how scientists communicate quantum algorithms and effectively program quantum computers today. Okay, so on the slide here, I present some other examples of circuits from algorithms for physical simulation. You can see every line in that circuit is a qubit. Every line from the left to the right to the page, every box or every dot is some logic gate that's going on. So I don't know about you, but I would hate to be a programmer who is in charge of implementing a program like this one, making a mistake somewhere, and then having to figure out where I went wrong. Okay? So the question then that a lot of programming languages researchers have asked is, can we build higher level quantum programming languages that feature cool abstractions that let us get around this problem? There's been a lot of progress on this front in this community over the last few years. What we've actually been able to do is to come up with this next generation of quantum programming languages that introduces abstractions such as if statements and for loops that you can actually use to express control flow rather than hardware. Okay? This is really great, but the existing languages still have a bit of a problem, which is that if you compare them to essentially any classical programming language, their capabilities pale in comparison. Right? Control flow is kind of widely considered a solved problem in classical programming. Why is it so hard to implement such a fundamental idea on a quantum computer, and how do we get across this expressivity gap? Well, we answer that question in this work. And to give you a hint, it has to do with the way that we reason about and compile the quantum programming languages. All of the languages that I just showed you have the property that they take a high-level control flow construct, like an if statement, and compile it pretty much directly to a logic gate or a sequence of logic gates in a circuit. So this nested if statement just turns into a single logic gate that's controlled on 2 qubits, a very hardware-level translation. But that's not how classical programming languages work, right? They tend to assume the existence of a CPU with a program counter and a conditional jump instruction. And this instruction forms the compilation target of basically every control flow construct that we know and love. It'd be really cool to just be able to do this on a quantum computer. But what we show in this work is that that's not going to work. We show that a quantum computer fundamentally does not support the conventional notion of a conditional jump. We show, however, that they are going to support a reinvented concept of a conditional jump that satisfies additional properties. We'll end up formalizing all of this through a complete specification of the forms of control flow that you can actually realize on a quantum computer, and an instruction set that enables us for the first time to implement control flow and pave a way forward towards extending quantum programming languages. So let's get right into that first claim. Okay, I want to be more concrete about what it means to not support a conditional jump. So what even is control flow? Well, here's a very small example of a program. Here you can see it's got an if statement and it's doing something inside each one of the branches. Okay? Now, I'm going to feed this program an input, and I'm going to expect it to give me some output. Okay? And so I have some values of x and y and some corresponding output values of x and y. And the way that the program will execute is that it's got this program counter register, which starts on line 0, and then in this case, due to the value of x, skips to line 3, and then eventually goes to line 5, and the program halts and gives the right answer. Okay? That's how classical control flow works. Nothing interesting there. But of course, on a quantum computer, the whole point is that we want everything to be in superposition. Okay? So now instead of just feeding in a single value of x and y, we're going to feed in a superposition of x and y. Remember that ket notation from before. All we're saying here is that we've got a whole bunch of qubits that are encoding states of x and y that are 0, 3, and 3, 0 at the same time. There is still that amplitude and that minus sign. We're not going to focus too much on exactly what their values are, but they have to be there, right? They kind of characterize what a superposition is. All right. So how can we execute this program by the analogy of what we did before? Well, we're going to start with line 0, and then something very interesting happens. Because x is now a superposition of 0 and 3, which means that conceptually we're executing 2 lines of the program at the same time. We have a superposition of the program counter. Okay? So this is all fine and good. It's a reasonable specification for how to do control flow and superposition. We're going to need to compile it down to the explicit instructions that actually manipulate the program counter to get that step to work, to take the program counter and put it into superposition. And it is, in fact, this instruction that will end up showing cannot be physically realized on a quantum computer. So that's the formal statement that I want to make. Let's get into a little bit about what the proof of this claim looks like. I'll do that by showing you a couple of previously proposed or conceived approaches for how to realize this form of control flow on a quantum computer and why they do not work. One of the first things that you might think to try is, well, I told you about this measurement operation, right? Why don't we measure the value of the variable, get a classical answer, and then use that to perform the control flow? The problem is that, supposing that we start with some data in superposition for the variable x here, Measurement will cause it to become a classical state with some probability. So maybe it just becomes 0. And then, of course, we can execute the rest of the program and we'll get some answer. But as you can see, the program has just become classical at this point. Right? There is no superposition anymore. The algorithm cannot possibly get any advantage over a classical algorithm if we're just performing measurements willy-nilly. In general, doing this is going to cause a quantum algorithm to completely lose its computational advantage. Based on this observation, what we have to realize is that a quantum computer fundamentally restricts the kind of operations you can perform on the data inside the machine without collapsing its superposition. Mathematically, the operations you can perform on quantum data while preserving its superposition are called unitary operators. Right? What is a unitary operator? Well, it has a mathematical definition. We could get into that in the paper. But the only thing that we actually really need to know about a unitary operator is that it is an invertible mathematical function. And what that actually means is that if you think of the semantics of a quantum program, or any line or any instruction in a quantum program, the denotation of that program or instruction has to be a unitary operator that is reversible. You should be able to conceptually go either from the input to the output, or if I give you the output, you should be able to tell me exactly what the input was. There's this one-to-one relationship between them. So that will actually be the first property that we need to enforce. The semantics of every statement or every instruction in how we program a quantum computer has to be reversible. There's another property. Let me tell you about that one next. And to do that, I'll dig up this state from a few slides ago where we had the superposition of the program counter. Let me blow up that state. And you'll notice that I have hidden the 1 over square root of 2 and stuff. It's not so important here. The important thing to note about this state is that, well, it's telling us about the state of the program counter and the data registers x and y. Now, when we program a computer, we generally want to just work with the data. We want to produce an answer that is just the data registers. Typically, we'll execute the program, get some final program counter, and then disregard that program counter and just return the data. Quantum algorithms want to do the same thing. They want to be able to just talk about that data and return it. But how do we actually do that? We kind of have to explicitly get rid of this program counter. It's a kind of a counterintuitive thing to think about because classically, well, of course, you just delete the data. You don't care about it. But how do we delete quantum information? Is that even a thing that we can do? Well, one thing we can try to do is to measure it, right? Measurement will allow us to turn quantum data into classical, but something very bad happens if we try to measure the program counter here. A phenomenon called quantum entanglement kicks in. You may have heard of this concept. It states that in certain quantum states, measuring a part of the quantum state will collapse the superposition of not only the part that you measured, but the entire state. So if you try to get rid of the program counter here by measuring it, or even via more other underhanded techniques like throwing it out or pretending that it never existed or whatever, quantum mechanics will dictate that the result is that the superposition of x and y, the data you care about, will also collapse. If you prefer a more mathematical presentation, you can think of entanglement as saying, well, I have this quantum state that has the program counter and some data registers. Can I write that quantum state as a tensor product of just the program counter and then a bunch of data registers? An entangled state is one for which this is not possible. We're going to want a state for which this is possible, which is called a separable state. Okay? That will be the second criterion that we need. We need a state that ends up being separable so that we can get the data out and leave behind the control flow. All right, so we basically now have all of the ingredients to show why we can't do a conditional jump on a quantum computer. If we look at the semantics of a program that uses conditional jumps, or jumps in general, we can ask the question of, is the way that the state of the machine evolving through time as we execute these instructions, is that evolution a reversible process? And the answer is no. It is not. You can come up pretty easily with examples where you have two distinct initial states, and then you execute one line in your program, and they go to the same final state, which indicates that, in fact, this is not a reversible process. You might be thinking at this point, surely there are some workarounds that you can do to overcome this problem, right? Prior work, for example, has proposed a very simple solution of just writing down the old values of the program counter. Right? So if you see, if we maintain this history of the old program counter being either 2 or 4 in this case, then you'll see that given the distinct inputs, they'll always go to distinct outputs. So now we have a function that is reversible. But is it going to satisfy that separability property? Well, to see why it doesn't satisfy the property, let's look at this, which is the state that we want. Right? We want the output state to have the x and y's in this way. And if we apply that trick of writing down the histories, this is the state that we actually have. I put the histories there in orange. What kind of state is this one? It is an entangled state. You can tell that it's an entangled state because if you look at the value of each branch of the superposition, on the branch where I know that PC prime equals 4, I know that x equals 0. And on the other branch where PC prime equals 2, I know that x equals 3. According to quantum mechanics, this means that if I measure one of those variables, I will also learn information about the other one, thereby collapsing its superposition. The result will be that no matter what I do, I can't get the data out of this computation without losing its superposition and destroying the advantage of the quantum algorithm. So that was, in a nutshell, the proof idea for our claim that you can't do a conditional jump on a quantum computer. Of course, there's a formal statement and proof in our paper. But what I want to move to now is some implications of this idea. So back in the 1930s, we figured out as computer scientists how to stop programming in terms of hardware level abstractions, like zeros and ones and noughts, and move to higher level abstractions like the lambda calculus. This has had implications for programming languages and computer science. It would be really great to be able to work with quantum computations like this too, to be able to stop talking about superpositions of zeros and ones and instead take arbitrary objects and give them the ability to exist in superposition. I wish I came up with this idea. In fact, I was beaten to it by this really great paper back in 2004, which proposed a lambda calculus where you can take the terms and put them in superposition. But this story has a bit of a sad ending, which is that the author of this paper never showed how to take this calculus and actually compile it to a real quantum computer. In this work, we prove why, which is that we show that these sorts of lambda calculi simply can't be physically realized. And the reason is the same as we've discussed before. The process of beta reducing a lambda term is not reversible. Right? Identity function reduces to identity function. Identity applied to identity reduces to identity. Okay? This is fundamentally not going to work. So what our work really shows is that reversibility is a barrier towards programming a quantum computer. We view this as an organizing result that states that quantum programming languages aren't going to get better unless we radically rethink our abstractions. And I want to just give you a brief idea of how we might rethink these abstractions. Okay? The problem that we encountered, right, is that sometimes we can be sitting at a line in a program, like line 5 here, and not know where we just came from. Right? That's that reversibility problem. But what if we had a new instruction set where every instruction tells you where you just came from? Where we made the targets of all jump instructions carry additional metadata that says, for example, in this case, if you're sitting on line 5, then this instruction, which you can pronounce as reverse jump to line 2 if x is not equal to 0, this instruction will tell you that if you're at this line and x is equal to 0, you must have just come from line 4. Or if x is non-zero, you must have just come from line 2. By doing this trick, you can essentially have a new instruction set that makes the semantics of every instruction reversible. Of course, there's a whole bunch of stuff that needs to go on behind the scenes to come up with a whole abstract machine that redefines jumps to make this happen. But the effect is that we can actually do this, right? We can actually come up with this reversible instruction set. The only thing that we need to do now is to also satisfy this separability property. And while the details are in the paper, I'll summarize it by saying that the key property we need to enforce here is just that while the program might manipulate the program counter however it wants in the middle of the program, by the very end, the program counter must be separable, not entangled with the data registers. And a simple way to do that is to just make sure that it's always equal to the same value on each branch of the superposition. In this example, we just say it's equal to 5 everywhere. The upshot of all this is that for the first time, we can now actually express control flow in a quantum algorithm without utilizing hardware-level logic gates, okay? Which is a very big improvement in our ability to program a quantum computer using high-level abstractions. There are a lot of open questions here. For example, how do we take this design and make it more practical in hardware terms? We don't know yet. We also don't yet know how to potentially generalize this idea to concepts that more resemble functional programming, while taking into account the impossibility results we showed earlier. But we do believe that this is a first step towards more expressive languages and tools to teach, invent, and analyze quantum algorithms. To summarize, I've shown you that in this work that if we program a quantum computer the way we program a classical computer, using the same sorts of abstractions, we'll end up turning that quantum computer into a classical computer, something that can't achieve any of this quantum computational advantage. But fortunately, we can build new abstractions that let us both harness this computational power and our wisdom in classical programming abstractions. That's the end of my talk. One last thing, I'm on the faculty job market this year, so if you think this research is cool and your department is hiring, I would love to chat. Thank you.
Thank you, Charles. Any questions? I'm sure Jens has a question.
But let me begin by saying, so people remember that Dijkstra had this paper called "Go-To Considered Harmful" in 1972. What's less known is that in 1973, Clark had a follow-up that was called "That's Fine, We'll Just Use Come From," and which seems to me to be what you're doing, that you have to explicitly...
There's something very, very poetic and about the way that this reverse jump operator is similar to that come-from operator. There are, of course, some formal differences, right? It is not a construct that arbitrarily transfers control, but rather a construct that says, transfer of control just happened. This construct is metadata that marks the way in which that transfer of control just happened.
Does it make programs long, to program in this style, does it add lines to the program, or does it just make the lines a little longer?
In our experience, the challenge is not really that the program gets longer, but rather you have to enforce additional properties on the correctness of your assembly code. Right? In classical assembly, if you have jump statements, the only thing you really need to worry about is that the target of your jump is a valid instruction. It's not like in the middle of an instruction or something like that. But now you have additional properties that say the target of a jump instruction must have the correct metadata that says, under this condition, you jump from there, and under another condition, you jump from somewhere else. That, in general, can be a little bit hard to write and to verify. And we've got some thoughts on how to make that process better, but it's still a work in progress.
Any last questions?
Hello, yep. The part about separability went by a bit fast for me, and I'm really surprised how you can achieve this. So if I understood right, I can jump anywhere that I want in the program as long as I have some final instruction at the end, like say line 99. And as long as we both end up there, we can jump any way we want. Is that correct?
That's the high-level correctness property, right? At the end of the program, like on, at instruction number 16,000, whatever is the end of the program counter, the line number for each branch of the program must be the same. It's achieving that property and making sure that every branch of the program achieves that property at the same time that is the difficult part. For example, you can imagine a loop that runs for a variable number of iterations depending on some value. And if it reaches the same line of the program but at different moments in time, that's a problem. So in our paper, we discuss why that's a problem and ways to overcome it.
Okay, yeah, thanks for that. That helps a lot. Could I just add padding to the shorter branches?
Yes, that is one of the things that you can do. Right.
Thanks again, Charles.
Thank you.